We're going to be talking about solving some first-order differential equations. And first of all, if we have a first-order differential equation and we solve it for the derivative, if the right-hand side ends up being just a function of t, these are the simplest to solve because I can solve this with direct integration. If I integrate both sides with respect to t, this one just becomes y, and if we did the antiderivative here, plus a constant, we would have that solved. So a couple examples of that. We've got the right hand side just a function of t, and so we integrate both sides and we have y equal, I need the antiderivative here, which is negative 1/2 cosine 2t and plus a constant. The right hand side is just a function of t, so I'm going to integrate both sides with respect to t. This one I can use integration by parts. I'm going to go ahead and use tabular, our little algorithm for integration by parts. So here's t, differentiate till I get to 0. Second column is the other function, e to the 3t, and integrate this until I fill out the table. And then I multiply this by a positive, this one by a negative. So my solution here is going to be 1/3 t e to the 3t, and then minus 1/9 e to the 3t plus a constant. So first thing is, when we solve for that derivative, if it equals just a function of t, just directly integrate. However, if we solve for that derivative and the right hand side ends up being a function of both t and y, remember y is a function of t, so direct integration is not going to work. So we're going to have a method that'll work on some of this type if they are what we call separable. So how do we know if they're separable? They are separable if that right hand side can be expressed as the product of a function of t and a function of y. And we're going to see the method in a minute, and you'll see why that would be the criteria for separable. But first we're just going to learn to identify those that are separable then. So are these separable? Remember, we're looking for that product of a function of t and a function of y. And it turns out that one of these, you don't have to actually have both of these in here. You could have a constant. For example, for h of t, it could be the constant 3, and you'd still be able to separate, as we'll see. So this one, is it separable? The answer is yes, because I could express this as negative t multiplied by 1 over y. And so my h of t is negative t, and my g of y is 1 over y. Is this one separable? Yes. H of t equals t squared, and g of y just equals y. Is this one separable? The answer is yes, but my h of t is just 1, and my g of y is this whole thing, y plus 1, and that way it is separable. Is this one separable? And the answer is no. It's the sum of t plus y, and there's no way to express that as a function of t multiplied by a function of y, because I have this sum. Okay, so if we do have a separable differential equation, let's see how we're going to go about solving it. We're going to start with this separable one. It can be expressed as a function of t and a function of y. And the first thing we're going to do is look at any equilibrium solutions. Remember, an equilibrium solution is something where it's not changing over time, and so it's not increasing or decreasing. So it would be where this function of y equals 0, because then we would have the rate of change is 0. It's not changing, so it's staying constant, and so therefore in equilibrium. So we would first look for any equilibrium solutions. After we've found those, then we could say, okay, we've looked at the case where g of y equals 0, so now we're going to assume it's not 0. We then would be able to divide both sides by it because it's not 0, and we would have it looking like this. We could then, just to make this a little simpler, call this some other function of y instead of having to write 1 over g of y. So we're just going to call that p of y. So we would get it to look like this. And then what we're going to do is let y equal phi of t represent a solution to this differential equation. Well, if it's a solution, I should be able to substitute it in here and I would get a true statement. So let's do that. So we have p of phi of t, and then I need the derivative dy dt, so we're just going to write that as phi prime of t, and that would equal h of t. And we know this is true because it was a solution. So now let's integrate both sides with respect to t. And if we look here to kind of see what we have, this side is just the integral of h of t dt. But on this side, if we look at this, if I took this y and I figured out dy, that's going to be phi prime of t dt. So I could replace this with dy. So let's do that, and when I do that, I'm going to go ahead and replace this back with y because y does equal phi of t. So here is our p of y, this is dy. So essentially what's happened here is we have shown that if we have a separable differential equation and if we manipulate it so the function of y is on the left side, we can think of it in terms of differentials. We can put a dy, the dy over here and the dt here. So if we think of taking this in terms of differentials, that puts the dt over here, and then we can integrate both sides. And what we have then is we're integrating the left-hand side with respect to y, and we're integrating the right-hand side with respect to t. So let's summarize this method. We first want to find any equilibrium solutions by setting the g of y part equal to 0 and solving. These would be anything then where it's not changing. Then we rewrite the equation in separated or differential form. So in order to do that, we're going to divide by that function of y, and we are going to split this in differentials, and we're going to have dy and dt, and we are going to integrate each side. We're integrating this side with respect to y, this side with respect to t, and when we do that, we will generate a constant of integration for this side and one for this side, and we can combine those constants and just call them c. Then, if possible, we're going to solve for y. And we say if possible because sometimes it's impossible to explicitly solve for y, but we want to do that if we can. And then the last step is if we have an initial value problem, we need to use the initial condition and find our c. So this is summarizing the method. Let's see it in action. So let's solve this differential equation by separating variables. Are there any equilibrium solutions? Yes, if we set our function of y equal to 0, we basically get y equals 0. So there is an equilibrium solution. Seems kind of trivial, but y equals 0. That solves the differential equation and it stays at 0. Then we're going to rewrite it in separated form. So we write our dy on this side with our function of y, so we'll divide both sides by y. And then we have negative 2t, and our dt is on this side. Then we're going to go ahead and integrate each side. So we're now basically after the antiderivatives. So this side is going to be the natural log of the absolute value of y. And we won't put our plus a constant because we'll combine it over here. So this is going to be minus t squared and then plus a constant. Next step, if possible, we want to solve for y in terms of t, and we actually can do that here. We can exponentiate both sides so that we can get rid of this natural log, and then we would have y equals e to the negative t squared plus c. We'll call this c sub 1, and it's actually a common trick to do this. You could write this as e to the negative t squared e to the c1, because rules of exponents, if we were to combine here, we would keep the base and add the exponent, so we're just going the other direction with it and we're splitting it up. And this is e to a constant, which is just simply a constant, and so we can just call that whole thing c. So our final answer is c times this, so we'll put it out in front, c e to the negative t squared. Now let's just look here. Here is the slope field or direction field for this differential equation, and we can see the solutions in that. And this would be to express all of those solutions. And then we could choose an initial value. If I said that y of 0 equals 2, then we could go ahead down here and say y of 0 equals c e to the 0, and that needs to equal 2, so that means c would be 2 since this is a 1. So there could be a specific solution for an initial value problem that would be y equals 2e to the negative t squared. So if we're given an initial value, we can actually identify the solution curve, which looks like this. Can we solve this one by separating variables? The answer is yes, because I could express this as t squared and then multiplied by 1 over 1 minus y squared. So yes, it is a function of t multiplied by a function of y. Are there any equilibrium solutions? Those would come by setting the function of y equal to 0, and here is the function of y, and that never does equal 0. So the answer is no, there's not any equilibrium solutions. So let's rewrite it in separated form. So we're going to have our dy on this side, and we're going to bring our function of y over there, so that would be by multiplying both sides by 1 minus y squared, and then we've got our t squared, and we put our dt here. Then we are ready to integrate each side, and when we do that, this is going to be y minus 1/3 y to the third, and that would equal 1/3 t to the third plus a constant. And then if possible, we want to solve for y in terms of t, and you can see in this particular case it is not possible because I can't explicitly solve here for y when I have a y to the third in one term and a y in the other term. Looking to see what these solutions look like, it's kind of interesting. Here are some different examples. You can see the red one is when our c is -3, and when our c is 0 we get the blue one. When our c is 2 we get the green one.